Satellites are important for communication, for navigation, and for just general Earth observation, and the case of monitoring our weather. We're going to take a look at satellite orbits and define different types of orbits, such as low Earth orbit or geostationary orbit, and see how we can use the laws of physics to describe the period of the orbit, the radius of the orbit, and the energy of the orbit. So, looking at these satellite orbits, we can understand that a satellite is actually an object in free fall. Think about a projectile. We launch a projectile, and it's going to generally follow a parabolic path when we compare it to the surface of the Earth. We're very close to the surface of the Earth, and it's fairly flat compared to the distance that the projectile will travel. Now, as the projectile gets more and more velocity, gets more and more energy, its trajectory, the radius of curvature of its trajectory is going to get larger and larger. We can imagine if we could give a projectile enough velocity, the curvature of its trajectory could become larger than the radius of the Earth, in which case the projectile will never hit the Earth again. It will simply orbit around the Earth. So again, a satellite is basically just a free-falling projectile, except the radius of curvature is so great that it never intersects with the surface of the Earth. Our most famous and largest of all satellites around the Earth is, of course, the Moon. We say that natural satellites, or moons, are basically objects that form around some central body. In this case, we have the Moon, which is 1% of the mass of the Earth, and it orbits the Earth. Just like the Earth would be a satellite of the Sun, the Earth is thousands of times less massive than the Sun, and the Sun is a central body there. In orbiting, it should be noted that if the satellite becomes appreciable in mass compared to the body that it orbits, that the body that orbits will actually wobble or actually orbit the barycenter, the common center of mass of the entire system. But for most of the satellites that we talk about, the mass of the satellites are so much less than the mass of the Earth or whatever other body that they're orbiting that this really isn't a problem. A little bit with the Moon. The Moon is, obviously much more massive than any other satellites that we put up there artificially. Of course, the first artificial satellite was Sputnik. This was launched in a low Earth orbit. So it was launched very close to the top of the atmosphere. It's actually orbiting, or started orbiting, within the outermost part of the atmosphere. This was launched in 1957. Not very impressive by today's standards. It was actually launched on what we would consider to be a modified intercontinental ballistic missile, about 84 kilograms and about 2.5 meters long, with just a very simple radio transponder. The International Space Station is currently the largest artificial satellite at 200,000 kilograms. It has immense dimensions. It's almost as big as a football field, 73 meters by 45 meters by 28 meters. And like Sputnik, it orbits in low Earth orbit, which means that it orbits high enough that the atmospheric drag is going to slow it down and bring it back to Earth anytime soon, as long as we keep boosting it up. But it takes about 92 minutes to complete one Earth orbit. And there are actually websites that you can find and watch the space station go overhead during the nighttime. It looks like a bright star as it makes its way overhead. Now, in terms of the total number of satellites, there are approximately 8,377 active satellites. The last time that I was able to retrieve this number. Most of these satellites, although the numbers that I'm showing you here are 2022 numbers, so these totals are going to be less than the total right here. Most of them are communication satellites. Right now, SpaceX is putting up a huge constellation of internet communication satellites known as Starlink. Amazon will be doing the same with their Kuiper. And there are a few other companies that are also putting up these constellations of thousands of satellites to provide internet for any location on the Earth. About 1,000 of the satellites are Earth observation satellites, including weather satellites, satellites that are just, observing properties of the ocean, properties of land. About 385 are basically demonstrating new technologies. Of course, GPS is a very, very important satellite, or is based on a very important satellite technology. So about 154 of the satellites are up there for navigation and position. And then in terms of just pure research, about 22 for earth science and about 18 for other purposes. I noticed they don't have any intelligence satellites listed in this. I retrieved this from the Union of Concerned Scientists. So I'm not quite sure whether spy satellites would be considered Earth observation satellites or technology satellites. There's certainly more than 18 spy satellites up there for the purpose of intelligence. In any case, communication satellites, of course, can occupy a number of different orbits. Again, these constellations for internet access are usually low Earth orbit because they want the distance between the Earth and the satellites to be very small, and that makes the latency also very low. Communication satellites also can orbit in a geosynchronous orbit. We'll talk about this a lot later on. And the idea here is that as the Earth turns, if the satellite is just in the correct orbit, it will rotate with the Earth. The Earth actually rotates a little bit less than 24 hours. But if the satellite rotates with the Earth, it can stay over the same part of the Earth both night and day. This is important for weather satellites, communication satellites, where you want to bounce signal off of a known point in space. So again, weather and communication satellites generally are put in this much higher orbit, what we call a geosynchronous orbit. They orbit about once every 24 hours. I think the Earth actually rotates 4 to 6 minutes less than 24 hours. And that's because when we think about the day being 24 hours long, that's due to the combined spin of the Earth on its axis, but also the movement of the Earth around the sun. And again, communication satellites want to be moving with the Earth because on the ground, if you have a satellite that moves with the surface of the Earth, you can always point to the same part of the sky. And this is the basic principle behind things like DirecTV or other satellite television, where a stationary dish can be used and you don't have to worry about a dish having to track individual satellites. So again, basically, if we look at the overview of satellite orbits, most satellites are actually in low Earth orbit. Why? Just because it's very inexpensive to do that. But also, if we're using this for a constellation of satellites, the shorter distances result in lower latency. Medium Earth orbit is probably the most unusual orbit. This type of orbit can be used for a number of different purposes. I'm wondering if a lot of these are polar orbiting satellites. But by far, the second most common type of orbit is the geosynchronous orbit, where we can place a weather satellite or a communication satellite in a stationary position above the Earth. And if it's a weather satellite, it's always watching the same part of the Earth. For instance, there's a GOES East satellite, there's a GOES West satellite that watch the East Coast and West Coast, respectively, of the United States. And any pictures that you get of storm fronts or hurricanes or other phenomena when you're watching your weather, these are actually coming from these GOES satellites. So the simplest type of orbit that we can imagine is a circular orbit, and the circular orbit will always have a constant velocity, and therefore the force is going to be constant, the radius is going to be constant. Um, basically, these are the simplest types of orbits to describe. If we take a circular orbit, we can say, okay, the circular orbit, will have a centripetal force associated with this. If the satellite were under no forces, it would just travel in a straight line. But of course, anything moving in a circle will have a force equal to the mass times the velocity squared divided by the radius of the path. So this is the satellite's mass, small m. We know by Newton's universal law of gravity that the universal gravitational constant times the mass of one object times the mass of the other object divided by the radius squared is going to give us the weight of the body. And if we set these two equations together, we can actually take the mass of the satellite and divide it from both sides, so it comes out of the equation. And what this shows here is that the general properties of an orbit are independent of the mass of the satellite. When this is taken out, we'll multiply both sides by r. This gives us the equation that v squared is equal to g. M represents the mass of the Earth divided by r. Okay, r is the radius from the center of the Earth to the orbit itself. And we get that our velocity is equal to square root of g m over r. So what we see here is that as the radius of the orbit becomes larger and larger, the velocity of that orbiting satellite is going to become less and less, which is interesting because if we look at the overall energy of a satellite, it actually gains more energy as the radius gets larger and larger because you're getting out of this potential well, but it loses kinetic energy, okay, as it gains potential energy, and that's why the velocity goes down as a function of the radius. So let's take a look at a typical value for a low Earth orbit velocity. We can see here that, again, the velocity is equal to square root of g m over r. We plug in our numbers. There's the universal gravitational constant. Here's the mass of the Earth. Here is the approximate radius of an orbit right above most of the Earth's atmosphere. And yeah, we're traveling about 7.65 times 10 to the 3 meters per second. So just to give a comparison here, the speed of sound is about 340 meters per second. So, at this type of orbit, at this low Earth orbit, we're going about a little bit more than 20 times the speed of sound. So again, not surprising that we need immense rockets to put, even the smallest satellites up in orbit, because once they're up in orbit, their velocity at 20 times the speed of sound implies a very, very large kinetic energy. The period for a circular orbit, we can take that equation and manipulate it just a little bit more. Again, circular orbits are very easy to deal with because circular orbits have a distance of 2 pi r. The circumference of the orbit is 2 pi r. If we take the velocity as being the distance traveled divided by the time, this means that the circumference of the orbit divided by the period of the orbit, how long it takes to make one complete orbit, is equal to the velocity. So I'm going to take this and replace that with my velocity. If I square the velocity, I get this right here. So I'll place that on the left-hand side of the equation. And here I see a relationship between the radius of the orbit and the period of the orbit. In fact, if I multiply both sides by r, I'll put r over here, divide both sides by t squared, I get a very interesting relationship where the period squared is proportional to the radius of the orbit to the third power. This is what we know as Kepler's third law, and we'll be revisiting this in the next section. So again, if I want to calculate the period of the orbit, just take the square root of both sides. It's equal to 2 pi times the square root of the radius of the orbit, cubed divided by g times m. So obviously, as we get a larger and larger radius, the period is going to become longer and longer, whereas the period of a geostationary orbit is going to be, about 5,500 seconds, which is roughly about 93 minutes. Again, the International Space Station orbits about once every 92 minutes. If we take that as sort of the smallest orbit that we can have, and therefore the shortest period, as I increase my radius, my period of the orbit is going to become longer and longer. Now, if I orbit over the equator and I say, I want my period to be 24 hours, a little bit less than 24 hours, such that my orbit is going around the Earth in the same direction that the Earth spins on its axis, I will get my geostationary orbit. And again, here we can see two satellites orbiting above the Earth. This is an image from Wikipedia. And this sort of represents what two satellites, like two weather satellites, would look like as they orbit the Earth, looking at stationary points on the Earth's surface. So again, if I set t to be equal to roughly 24 hours, okay, I can solve for the radius that I need to get to that particular orbit. Again, here's the radius of my orbit. Notice that I'm solving for r based on t. So I'm going to put t on the right-hand side of the equation. I have r cubed proportional to t squared. So to get rid of the cube, I've got to take the cube root on both sides. And when I plug in all my numbers, g, the mass of the Earth, the time for a geostationary orbit, divide that by a constant 4 pi squared, I get that the radius is 4.21 times 10 to the 6 meters. So it's larger than the low Earth orbit considerably. And again, if we go back to the low Earth orbit that we calculated before, where we had 6.8 times 10 to the 6 meters, here we're increasing our radius to 4.2 times 10 to the 7 meters. So not quite a factor of 10, but considerably larger. This geostationary orbit means that I need to put a lot more energy into the satellite in order to boost it up to that geostationary orbit. So, normally when somebody pays for a satellite to be placed in orbit, they'll pay, some launch company, ULA or SpaceX, to launch their satellites, and they'll be given a fee. You'll be charged so much for a low Earth orbit and a particular mass, and obviously for geostationary orbit, there's going to be a lot more energy involved. Now, talking about the energy of the orbit, we've already said that the velocity decreases as the radius becomes larger and larger. And what this means is, as I get into a larger and larger orbit, what tends to happen here is the kinetic energy is going to decrease inversely proportional to the radius, okay? Well, what's interesting is the energy for an orbit, the potential energy for an orbit, is negative gm capital M over r. So as the kinetic energy is getting smaller and smaller, the potential energy is negative gmm over r, is getting less and less negative. It's getting larger, closer and closer to zero. So if I take the potential energy plus the kinetic energy, I see that the total energy for a circular orbit is about negative 1/2 gm m over r, okay? So in looking at the energy for a circular orbit, the absolute value of the kinetic energy is about half the absolute value of the potential energy. But remember, the potential energy is always negative for a bound system. So again, the total energy of the system is negative 1/2 gmm over r. The kinetic energy is 1/2 gm big M over r. and the potential energy is negative Gm capital M over R. So essentially here, again, the absolute value of the kinetic energy is going to be half the absolute value. The absolute value of the kinetic energy is going to be half that of the potential energy. But again, the potential energy is always negative for a balanced system. Here's what the energy well looks like for a typical orbit and a typical planet. We can think about when we launch a satellite in orbit, it's sitting at the bottom of this gravitational well. Okay, this is where R is equal to the radius of the Earth. As work is done by the rocket motors and it gets going faster and faster, we climb out of this well. But basically, once we're locked in orbit, we have a fixed amount of energy as long as there's no drag force or anything else that's going to pull on the satellite. Once it gets a circular orbit, it's moving at a constant rate because the potential energy is remaining constant. And of course, that implies that the kinetic energy is also going to be constant. Okay, so here the energy is equal to the kinetic energy plus the potential energy. It's equal to negative 1/2 G small m big M over R. Okay, it should actually be small r because big R usually implies the radius of the orbit. But basically, as R becomes larger and larger, we get closer and closer to a total energy of zero. And one can imagine if we can get an infinite distance from the Earth, that the gravitational force would drop to zero. And again, the net energy would be zero also. Now, a circle is actually an ellipse. It's a type of ellipse where the semi-major axis is the same as the semi-minor axis. And most satellites that are up there are actually in circular orbits, which are essentially, again, a very round ellipse. I don't know if that's a proper description for an ellipse. But we can actually stretch this semi-major axis. The semi-major axis for this orbit would be from the center right here to this point right here. The semi-minor axis is right here. And in an elliptical orbit, the body which is being orbited sits at one of the foci of the ellipse. So in this particular case, the satellite would, if it's going around the Earth, we call the closest approach, we call that perigee. And as it goes to the greatest distance, we call that apogee. So again, the Earth would be sitting here. Nothing would be sitting at the other focus. The satellite would speed up as it approaches the focus and then slow down as it goes away from the focus to conserve energy. And what that looks like is something like this. At perigee, it is deep down in the potential energy well. Here's where it's going the fastest. So at this point right here, and as it climbs out of that well, it reaches a maximum distance, which we call apogee up here. But essentially, the total energy of the system has not changed, okay? The energy is the kinetic energy plus the potential energy. And essentially, this R right here would represent the radius of the semi-major axis in terms of the total energy of the system. Now, there are many shapes of orbits that we can have. This red circle obviously represents a circular orbit. This ellipse is a somewhat eccentric elliptical orbit. Eccentricity talks about how stretched out the semi-major axis is compared to the semi-minor axis. Here's a very elliptical orbit, okay? But if I were to give my satellite enough energy, if I were to give it more kinetic energy than it had negative potential energy, I would have a free body. It would break free. When the energy equals zero, it would follow this parabolic path. And we call this an open orbit because essentially a parabola, unlike a circle or an ellipse, is not closed on itself. Once a satellite obtains a parabolic orbit, it is one and done. It is gone. Even faster, if my energy is greater than zero, my total energy greater than zero gives me a hyperbolic orbit. So for instance, when we want to send space probes to the outer parts of the solar system, we have to get the space probe going fast enough that it obtains a hyperbolic orbit with respect to the Earth, and we'll even use the Earth to give it, multiple boosts. In this case, every time it makes a pass, it's really passing with a hyperbolic orbit, still orbiting, kind of strange because it's still orbiting the sun in a closed orbit, but with respect to the Earth, it's an open orbit. Now, conic sections are the shapes of orbits. We've already seen we have circular orbits, we have elliptical orbits, we have parabolic orbits, we have hyperbolic orbits. If I take a plane, and we call these conic sections because you take a cone, and if I take a plane and I cut through this cone, the intersection of the plane and the cone will form a circle. If I tilt it a little bit at an angle, it'll form an ellipse. If I tilt it even more, it'll become a parabola. And with the greatest or most vertical inclination, it becomes a hyperbola. So all these shapes, we call them conic sections because we can create them by taking a cone and simply taking a slice through the cone. Again, a parabolic orbit would correspond to a total energy of 0. Here's where the kinetic energy would be equal and opposite to the potential energy. So our kinetic energy and potential energy are equal and opposite to one another. And, for that particular case, our kinetic energy at some distance would be equal to Gm over R. Okay. Hyperbolic orbits here, the total energy exceeds exceeds 0 or is greater than 0. So our kinetic energy is greater than our absolute value of the potential energy. And, you keep adding more energy, the hyperbola just becomes flatter and flatter and more eccentric. Now, in 2017, a new asteroid was discovered, and whenever we find a new body, a new asteroid, a new comet, we want to chart its orbit to sort of figure out, well, where's this thing headed? We're always in the back of our minds, hoping that it's not headed for Earth. But in this particular case, when they plotted out the orbit, the expectation was you always get an ellipse because usually an asteroid or a comet, well, they orbit around the sun, and those are closed orbits. However, this one had a hyperbolic orbit. This is very important because what this indicated is this was a one and done orbit. It was passing through our solar system in 2017, and it was never going to return again, implying that it came from outside of our solar system. There are all kinds of conspiracies that were associated with this, but basically, it's not beyond the possibility that an asteroid or comet from another system could have gone too close to another planet, too close to another body, gained too much momentum and energy, and was therefore ejected out of that particular star system. So these bodies, basically wander through the galaxy. They're not attached to any star system. And this particular one, 2017 U1, was the first body discovered to have originated not from our solar system, but from someplace else.